Welcome all to the seventh Fusion EP talk that will be given by Katia Camacho, who's a former student from UNAM in Mexico, one of maybe the main public university, right? Or main
Yes.
university, probably the main university in Central, maybe Latin America. Okay.
It's on the
And
top
then
three
she
most
went
of the time.
on to, well, she already did some work in Fusion back then, related to stellarators, specifically to TJ2, if I recall correctly. And then went on to the Fusion EP Master on her first year in Ghent University, and then to Nancy, where she continued working on the stellarators. And now I'm gonna let her give you more details on her academic trajectory.
Well, I guess you covered most of it, but yes, I did my bachelor in physics in Mexico in UNAM, the National Autonomous University. Then there is a small group working on fusion there, so I did my bachelor thesis with them. Then I did my master in the EP Fusion program, and yeah, I've always been interested in stellarators, so I kept working on that. And now I'm gonna start a PhD in the next months. And yeah. To get to the presentation, what I'm going to talk about, the work I'm going to present is a big part of what I was doing during my master thesis, and also a work I was doing in an internship in the last couple of months. So I was doing it in the Institut Jean Lamour in Nancy in France, under the supervision of Dr. Erwan Derias. And yes, well, first, it's quite a long title, so I would like to start by explaining the little parts of it. So first, I guess almost everyone here is familiar with fusion, but I'm just going to give a very fast introduction on what a stellarator is. So stellarators are a kind of magnetic confinement configuration for achieving fusion. One of their main characteristics is that they are truly 3D magnetic geometry, meaning that they don't have any symmetry, as the case of tokamak, that is the most used configuration for fusion, and also that there is no need to drive a current around the plasma, and this gives them a lot of advantages. It allows for continuous operation, and it also reduces the instabilities on the plasma associated to this current. But one of the drawbacks of this design is that you need it's very complicated to design and to build, but advances in computation and computer calculations have made it easier to be done nowadays. But still, it's much more complicated than the design of a tokamak. And this is mostly because stellarator geometry doesn't guarantee on itself a confinement. That means that particles can go out of the plasma and go to the walls of the device, and that's not what you want. So there's several ways to attack this problem, and one of these is to use quasi-symmetry, that is to try to make our magnetic configuration as close to a symmetric device as possible. And the one we are interested, because that's the device I'm going to be talking about, is quasi-actually symmetric. In this kind of symmetry, our magnetic field only depends on the radial coordinate, and also depends only on one of the angular coordinates, on the poloidal coordinate as is indicated in the figure. So then I would like to talk about what is the quasi-actually symmetric stellarator STEL. A STEL is a specific magnetic configuration that was found that presents good confinement conditions. The STEL stands for Evolutive Stellarator of Lorraine. This is a small-scale experiment that was developed in the University of Lorraine. And it was one of the benefits it has is that it has relatively simple coils. It would be kind of easy to build compared to other stellarators, but it doesn't give very high pressure, so it's not convenient for using it as a fusion reactor, but it would be very useful for studying turbulence in this kind of configuration, especially because no stellarator configuration of this type has been built yet. And we expect this kind of geometry to, well, it's very similar to a tokamak. So we expect that it will have the good confinement of tokamaks, but it hasn't been studied in detail yet. And it was originally expected to be built in the University of Lorraine, but it was canceled due to budget cuts. And yeah, but a couple of other universities have been trying to build something based on this configuration. I've heard of a university in China, and also some people in Costa Rica who are trying to build a stellarator based on this configuration. And then regarding the part of the title that refers to the currents and to the electric fields, we are interested particularly in one specific kind of current that is called the bootstrap current. So I had said before that one of the benefits of stellarators is that they don't need an external induced current, but still, due to how the plasma behaves, we expect internal current to appear. This is the bootstrap current. It's predicted by neoclassical transport theory. And since stellarators are normally designed to minimize these parallel currents, there is not a lot of information on how much this current is going to have an impact on how the plasma behaves and on confinement. And also, since Estelle has a tokamak-like geometry, we expect the currents to be very high, so it would be relevant for this kind of device. So this bootstrap current can be expressed from transport theory as it is, well, shown here in this equation. It arises due to geometrical considerations, but also in the presence of density, temperature, and electric field gradients. So we need to consider all these quantities, but we also need to calculate the so-called transport coefficients. And in order to find this, we need to solve the drift kinetic equation, which can be solved analytically for very specific cases. But in the case of stellarators, due to the complicated geometry, we need to use computational tools to do it. And yeah, well, we're interested in calculating this current because it has this is going to be a toroidal current going through the stellarator, which is going to produce a magnetic field, that is going to have an impact on the field generated by the coils. And then it's going to find the magnetic equilibrium and probably have an influence on the stability of the plasma. So we want to see how big this impact is. But we also need to make what we call a self-consistent calculation. That is to calculate well, I will explain a bit more in the next step. Yeah, it will be easier to explain it with this diagram. So what we have is the method we use to make the calculations. So first we need to have like a magnetic equilibrium for the kind of device we're using. And this is done by using a program called BMEC that solves the MHD energy principle and gives us, well, we give this program the information about the magnetic coils that we're using and about what is the density that is circulating through the plasma, the current and the total toroidal current. And from this, we can obtain information about the magnetic equilibrium and how the magnetic configuration is going to look. So here, this image I had shown previously, this very colorful image, tells us how the magnetic field amplitude is on a magnetic surface in the stellarator. So yeah, the colors are coded by the magnitude, by the intensity. And so we need this information in order to later be able to calculate the bootstrap current, because this current depends on the geometry and how the magnetic field is behaving. But BMEC also gives us information about how the quantity called rotational transform, that I'm going to explain a bit more later, is produced. So we can also get this information from BMEC. And then having this magnetic configuration information, we can use a specific code that is called Sphinx that allows us to solve the drift kinetic equation numerically, and that is especially designed for the geometry of stellarators. It used Fokker-Planck collisions operator. The collision operator is very important for achieving good results, and this is the most advanced collisions operator that is considered in this kind of codes. And yeah, but in order for Sphinx to be able to calculate the current, we need to give also information about the electron and ion temperature profiles, about the density profile, and about how the electric field is behaving. But yeah, we're gonna talk more about the electric field later. But then once we obtain the bootstrap current from Sphinx, what we need to do is to give this information to the VMEC code that is gonna calculate again the magnetic configuration. And then with this new magnetic configuration, we again calculate the bootstrap current, and we do this process several times until neither the bootstrap current nor the magnetic equilibrium are changing. And this is what we call the self-consistent method. We could obtain self-consistent results. So, well, first, this is the result I had shown this image already before. It's how the magnetic equilibrium looks for this specific configuration. From here, well, we have on the bottom how the magnetic flux surfaces look. Here, it's important to show that they are like one circle inside the other, and that shows us that we are going to have their very well confined particles. And yeah, this is the result for the initial equilibrium where we're considering the current is zero. That is the way Estelle was calculated originally. Then the profiles we used in order to calculate the bootstrap current that we need to give to a Sphinx were this. We are considering a scenario where we are using for heating only electron cyclotron resonant heating. So in this case, we expect very high electron temperatures and very small ion temperatures with these profiles. And well, density, we expect it to be following this profile that's on the right. And the radial electric field that we originally used, we first consider that this we'll later see that this is not such a good assumption, because the electric field actually has a high dependence on the magnetic equilibrium, which is going to be changing in each iteration. But for first calculation, while I was doing my master thesis, we decided to go only for this, like considering only one radial electric field, because the calculation is quite time consuming. And well, I had a limited amount of time during the master preparation. Yeah, so this is the one we used. It's solved using another transport code called DKES. This result was previously calculated by people in IPP, in the Max Planck Institute of Plasma Physics before. So I just took this result to make my calculations. And these are the results we obtained for the bootstrap current, for how it goes changing. First, we have in blue, in the solid line, how the current is considering the original equilibrium. And there we expect a quite high current. The integrated current is around 100 kiloamperes, which is quite high, especially for stellarators. And yeah, but then we do this iteration process and we see that it keeps changing. Like the first iteration is very unstable, then as long as we go through the iterations, it gets more stable, and it also reduces the total toroidal current until we get to the self-consistent case, that is this light blue line with dots. That's after 8 iterations, and it doesn't change much from the 7 to the 8 iteration. The change is less than 1% in the total integrated current. So we consider that already our self-consistent solution. And yeah, we see that the total current is reduced. It's almost half of what it was from the original equilibrium, but it's still a substantial current for stellarators. But we also see that although the self-consistent current that we see has a very similar shape, like behavior radially with respect to the original equilibrium, we also see that there are certain discontinuities that we observe and that we weren't able to explain at that time. So what we said while I was doing my thesis is that, I'm sorry, going to this, that maybe these were associated to some transport barriers, but we weren't able to find a definitive solution. So what we decided that would be a good thing to do later is to consider the effect of the radial electric field. That is what I'm going to show a bit later. And then another important thing to consider on how the current is affecting the magnetic equilibrium, that's the stability of the plasma, it's to look on this quantity called the rotational transform. And the rotational transform gives us, well, it's what it's expressed here in the formula, but it gives us information about how many turns it takes in the poloidal and in the toroidal direction for a magnetic flux line to close upon itself. So it has been found that for tokamaks and stellarators, when this rotational transform takes values of like rational values, we can expect the formation of magnetic islands and of transport barriers, like regions where confinement it's not perfect, and this could have an impact on how the transport is behaving in the plasma. Suddenly you can have particles trapped in these regions, in these magnetic islands, and then they are sometimes beneficial, but also sometimes they can make the confinement worse, reduce temperature, make density worse. So it's important to see how this quantity is changing with the current. So here we see that STELL was originally calculated to have a rotational transform that was very small, but also didn't change much with the radial position. Here on the x-axis is the normalized flux. That's just a way of labeling our radial positions. So we see that originally it was considered to be like very small. It doesn't change much. It's around 0.2, is this blue solid line on the bottom. But once we are considering the presence of a current, this quantity changes dramatically and it's increased a lot. But it's not only increased a lot, but it's also changing with the radial coordinate. And then it has, well, for the first iteration is the worst situation, this orange line on top. But once we get to a self-consistent case, the change is not so big as with that first iteration, but it's still quite dramatic. And we can see that these rotational transforms start taking, for different radius, values, rational values that could have a very bad impact on confinement. But okay, then we saw that we had some problems on how the current looked. The current profile doesn't look very soft. There is some problems with it. So what electric field to be constant through each iteration. And since it depends on the magnetic equilibrium, the correct way to do it would be to update it for every iteration. And yeah, well, we can use the Sphinx code to also not only calculate the bootstrap current, but also to find this radial electric field. So, well, just to explain where this electric field comes from, is that in 3D systems, as is the case of stellarators, particle fluxes are not ambipolar. They do not always compensate. So in some situations, you have electrons and ions moving at different speeds or moving differently within your plasma. Well, they always move at different speeds, but you have in the radial direction that electrons are flowing faster outside than ions. So in order to compensate that, the plasma generates a radial electric field that is called the ambipolar field. And there is different ways of finding it. The one we used for these calculations is to find the electric field for which the fluxes of electrons or ions are the same. So these fluxes can also be calculated from the transport coefficients, so are already calculated by Sphinx. So we only need to check for each radial position, make the calculation for different radial electric fields and see where the fluxes become zero. One of the drawbacks of this is that we find several roots. Normally there is 3 solutions for this equation. And one of these is normally an ion root, an unstable, and an electron root. So we have to choose using physical arguments the reason why we want to select one or the other root. The ion or the electron. Unstable root is never a physical solution. And well, this radial electric field then depends on on transport, which depends on magnetic equilibrium, and that's why it's needed to do it on every iteration again. So what we did was to calculate this electric field, how it was changing. So yeah, well, here first, the original equilibrium is in blue, the line, solid line on the bottom. And yeah, here we can see that we have first what we call the electron root, that is a positive electric field, and then it changes to the ion root on the negative, with a negative electric field. We did the, well, this is consistent with our temperature profiles. It is expected that for the kind of temperature profiles that we have, where we have a big difference in the center between the electron temperature and the ion temperature, that we're going to have first the electron root, and then the solution for the last part. These are then the solution that we have to choose is the ion root. So we decided to skip the first iteration calculation because the current was very unstable, as you probably remember from the previous graphs. And then we started on this, and then it was difficult for Sphinx to find a solution for the electric field. So we started from the second iteration, that is the yellow line, and we kept doing this iteration. The idea is to get also to the self-consistent case, but well, I am still working on these calculations, so I have gotten only until the 5th iteration, because it's a bit time-consuming. Root, and then to make the current calculations again, and it takes a while. So I've stopped here on the 5th iteration, which is still already very close to what we expect to be the self-consistent case. So here we see that the electric field is indeed changing. It's becoming much higher for the central region compared to what we have from the original equilibrium, but it's also calculated with a different program. This is calculated with Dicke and was calculated previously by some other team in Greifswald. So we see that this electric field is increasing a lot, but still it keeps behaving in the same way, which is consistent with the temperature profiles we have. And now the thing is to see how big of an impact this electric field has on the current. So we did again the calculations for the bootstrap current, seeing how, yeah, now using the correct electric field, the calculated field for each iteration. As I said, the 3rd iteration is just the same one as the previous one, but all other like 2nd, 3rd, 4th, and 5th iterations are the ones we did now with the correct electric field. And first, we see that for the first iterations, the profile is quite similar to what we had from the previous calculations, but we had these discontinuities on the center of the, like very close to the center of the plasma. But as we go getting in higher iterations, the profile starts looking very soft. We don't have any more these peaks jumping from one position to the other as we had when we didn't consider the electric field. So that's a very good result. We're seeing also, yeah, it's kind of too early to give any conclusion about this because the self-consistent current hasn't been achieved yet. I think we still need a couple of more iterations, 3 or 4 more iterations to achieve that. But well, the profile looks very similar to what we had before. And yeah, here, compare how this self-consistent current looks. It's the one we have in green for the case where we are not considering the electric field change. And when we are considering the electric field change, although we haven't achieved the self-consistent case, we are comparing to this. So it's not a very valid comparison yet, but it's just to see how we're going there. We see that the profiles are very similar, but we don't have those peaks anymore, which is a good thing because they were not physically explained. But we also see that the total integrated toroidal current is very similar. The difference is very small. So it seems like the electric field is not having a huge impact on the profile, neither on how big this current is, but it helps to give like better, softer results. And it's still smaller compared to the original toroidal equilibrium current. And then we also want to see how the impact on the rotational transform is, because even though the profile is a bit different, so maybe this will be having an impact on how the rotational transform behaves. And we see that this green result is considering the electric field is slightly higher than the previous rotational transform we had, but the profile follows pretty much the same behavior, and we still have this problem that, well, we still see that it's important to consider this current and equilibrium, because we are still crossing these rational surfaces that could be detrimental for confinement. And so I'm gonna just finish, say the conclusions. So we were able to calculate self-consistent bootstrap current, but we still need to do some more calculations to make the proper calculation, now considering the radial electric field. And we also find that these high currents have an important impact on the rotational transform, that it can go up to 3 times higher than the original results. And this could be very important because rational surfaces could appear, and then confinement is not what you originally designed your device for. And well, also it seems promising now, although it's too early to give any conclusions about it, that the current radial profile discontinuity seems to be solved by considering the electric field. And yeah, well, but we still need to work a bit more on this to have the calculations completed and to be able to give results, like concluding results about this. And yeah, well, just very fast to mention that calculations were done on the computers of the Max Planck Institute of Plasma Physics, and I was working there with the stellarator theory department, which helped using the Sphinx code. They are working on it, and yeah, give us the configurations for this for Estelle. And also that the last part of the calculations regarding the electric field impact were done on an internship that was funded by FuseNet. And I guess that's it. So any questions?
So thank you very much, Katja. And well, a true stellarator expert in the making. And yeah, now we're open for questions. So please go to the participants. If you go in the menu, you'll see a participants button, and there you can raise your hand if you want to ask a question. I think maybe we'll start with Neil, who definitely has quite a few questions.
No, that was also some comments for myself. But yeah, I have, for example, a question about bootstrap current, obviously. Can it be a good thing for a stellarator to have bootstrap current?
Yeah, it could be a good thing because there is not a lot of studies. We really don't know much how it's gonna behave. So far, people have tried to make it, to design their stellarators to have a very minimum current, but it could help like shaping your magnetic flux surfaces, and maybe help like this, the apparition of these magnetic islands they sometimes behave as internal transport barriers, so they help you to reduce your radial transport, so that could be a good thing for them. But yeah, I mean, it's not, there is still a bit more of experiments, I guess, need to be done for that.
Okay.
And yeah, and for example, with, okay, I guess that's it.
So I don't see another hand raised yet, so let's continue.
Right. Yeah, you said that Sphinx could be used for studying turbulence, right?
No, not the Sphinx. No, Sphinx only does like transport calculations.
Okay.
Yeah.
Makes sense.
I mean,
I wasn't sure.
Yeah, no, it's only for transport calculations. I know the thing is that Estelle, like the device, was one of the reasons why they wanted to build it, is because it would be a good device to study how turbulence behaves in that kind of geometry, which is something that hasn't been studied because there is no quasi-actually symmetric device built anywhere.
Okay.
So since you mentioned it, have you gotten in touch with people in Costa Rica who I think want to build such a,
No, not yet, but yeah, that's something I would like to do, because I've heard, I was checking some of the Latin American workshop on plasma physics of 2 years ago or something like that. That was actually here in Mexico, in my university. And yeah, they presented like the plan to build a stellarator based on this Stell design. So yeah, that's a very interesting thing. But yeah, I haven't had time to get in touch with them. I will.
Well, yeah.
We got a big list to check. So what's the next question?
No, I think this would be my last one. Yeah, this picture that we see a lot with the colors that represent the magnitude of the magnetic field on the flux surface, right?
Yes.
But to me, a flux surface is a surface on which the magnetic field is constant, isn't it?
No. This is just the magnitude of the magnetic field of this one, right?
Yeah, exactly.
Yeah. No. Well, a flux surface is like a region where your flux is constant. It's a surface where your flux is constant. And yeah, but yeah, also the magnetic field. This is just the magnitude of the magnetic field, not the direction. So that can also change.
Okay.
Yeah, this quasi-symmetry is only concerning how big your magnetic field is, not the direction of it.
Okay, so still no hands raised in the participants box. So I'll go ahead if that's okay. So when you simulate equilibria in tokamaks, I think it's customary to solve the Grad-Shafranov equation, which is like an ideal MHD equation for 2 dimensions. But of course, 2 dimensions would not be enough for a stellarator. Therefore, you need to solve the so-called energy principle, right?
Yeah, exactly. That's what VMEC does. That's the principle over which it finds this. And well, also an important thing there is that VMEC considers that these nested magnetic flux surfaces exist, like, because otherwise, yeah, you cannot. It's very complicated to calculate them because they don't exist a priori because the geometry is quite complicated, but it assumes there is some solution and it starts from there.
But isn't there like some kind of theorem in stellarator physics about the existence of those flux surfaces based on like the from the fact
part of your question?
Those,
yeah, no, well, for
yeah,
stellarators, unless you have these quasi-symmetry conditions or something else that they call homogeneity, I don't really remember the term, only under those conditions you can say that you will have the existence of flux surfaces, because then you have like another symmetry that you can exploit to have to prove the existence of those.
I see. Okay, so
yeah, it's not for any stellarator.
The classical stellarator doesn't guarantee the existence of flux surfaces.
Yeah, exactly. And that's why at the beginning it was very complicated because transport was very bad on the first experiments.
Gotcha. So back to my question. What I wanted to know is, how do you get to the energy principle? Do you get it from ideal MHD? Do you get it from kinetics? Do you get it
from ideal MHD? Well, and making certain assumptions.
So it's just like a more general Grad-Shafranov, or is it very different?
No, Grad-Shafranov also comes from MHD. It just makes more assumptions. So yeah, it's just kind of more general. But it's a different way of solving the problem, because then you have like an iterative process that you can use with numerical methods.
Okay. Thank you. So we have a question from Francis. So I'll let you go ahead and unmute yourself, Francis.
Hi, Katya. Can you able to hear me?
Hi, Francis. Yes.
Okay. So we consider the neoclassical transport. So and also we consider the profiles of density and temperature to be constant. So does it change due to neoclassical transport? Is it fine we consider the profiles to be constant doesn't need to be affected by this transport, neoclassical transport? Is it fine?
Yeah, yeah. In principle, they could change, but yeah, we are assuming the temperature and density profiles are mostly defined by how we are heating the plasma. So we're, yeah, I mean, if you want to do it like very, very well, yeah, they are going to change due to the to transport it.
Yeah, okay.
Yeah, we're kind of skipping that part.
Okay, yeah, okay.
Because we don't expect it to be so big.
So, okay, yeah, okay.
So do we have any more questions? If your microphone doesn't work, you may ask questions in the chat box. We're also monitoring this. However, if there's no more inquiries, I'll thank the speaker again. Thank you so much, Katya. This was very interesting. Oh, yeah. Question. Okay, are you able to read the question, Katya? Or maybe I'll read it for everyone.
Can you read it for me?
Yeah. How much more computing time do you think it would take to calculate a couple more iterations of the bootstrap current to be sure you've reached a steady state solution?
Yeah, well, this self-consistent solution. Yes, well, one of also the problems we've had is that the server was down for a while, so there was like 3-4 weeks that I couldn't do much calculations. So yeah, I guess I think I will be needing some around 3 or 4 iterations more. And yeah, I'm not sure about the computing time, but like in effective time, like work time, I guess in 2 or 3 weeks it should be completed.
Oh.
Yeah.
So, okay. So I think no more. Oh, one question from Jose. So Jose, go ahead and unmute yourself, please.
Yes, sorry because I missed the first part, but I have a small question. So the thing is that the magnetic field is higher in the inner part of the and not in other parts.
The magnetic field is going to be generated entirely by the coils. I don't have a picture of the coil geometry here, but yeah, with stellarators,
yeah, I know.
Find your.
So the point is that you fix the different currents for each coil, or each segment of the coil has a variation, or?
Well, I'm not really familiar with the design, like with the engineering design of it. But yeah, I mean, I could give you the paper where they explain yeah, it's a more technical document on how they are doing the calculations for the coils. Yeah, because I'm not sure how it works. Yeah. So.
Okay, thank you.
Okay. Hi, Katya. So sorry, I have one more question. Yeah. So can you tell about like what will be the next step? Like you in the starting you said it will be also used for turbulence studies. So can you tell how this will be related to that? Like how?
Yeah. Well, the idea of building Estelle was to have this kind of tokamak-like configuration where you can kind of have more control over your flux surfaces in order to study how turbulence behaves there, because we expect to have, well, they expect to have very similar situation as in the case of tokamaks, but since it hasn't been built, they don't know yet. So yeah, I guess it just depends on whether it's going to be built somewhere or not, but it's.
Okay. So, okay.
Yeah.
Okay. Yeah.
So we have another question in the chat from Sadiq. It says, thanks, Katya, for the nice talk. Do you have any idea of how to build that stellarator in order to have the axial symmetry?
What they didn't study, that's the study they did at University of Lorraine, to find the coil design that produces this kind of geometry. So I guess people there, and also people in Greifswald, in IPP, were working on this design. So they are the ones that have all that information regarding how it should be built. But yeah, I mean, part of the idea to have this configuration is that coils weren't extremely complicated. So they were going to be kind of easy to build for a small university, well, for a university scale experiment.
So how are the coils different from quasi-poloidal symmetry or classical stellarators or?
Well, in classical stellarators, what you have is like two different sets of coils, like some toroidal coils, as in the like to that one in the beginning, like that one, that you have like some coils going around the torus and some like the ones in green and the red coils. But in the case of Stella, as far as I understand, are modular coils. So coils are designed independent, like each coil that was designed for. It's just how, like, the shape of the coils and the kind of currents you're letting go through them. Yeah, but also because of that, you cannot achieve very high pressures because your magnetic field is not going to be that intense. So yeah, that's why it's not good for being a reactor, but it's good for some other studies.
Okay, but I think modular coils are not proper to a particular configuration. Doesn't Wendelstein 7X have modular coils too?
Can't hear you anymore. Could you repeat the question? Kind of cut.
You hear me now? I'm sorry, do you hear me now? Oh,
No.
yes? No? Do you hear me? Katya? Are we stuck again?
Yeah, I think this is Wi-Fi.
Katya?
Oh, I can hear you now. Yes.
Okay, we have a little unstable connection here, unfortunately. So I'll repeat it. So I think Wendelstein 7X also has modular coils, doesn't it?
Yes.
Like it's not proper to a form of symmetry. So I guess the question I was asking, trying to maybe specify a bit more on, expand a bit more on what Sadiq was asking is, how do you, like roughly speaking, what's the difference in shape between, I mean, maybe that's a little tricky, a little specific, but what's that?
Yeah. Yeah, the thing is you have to just make sure that your magnetic field, for this kind of axis symmetry, like actually toroidal symmetry, you need to be sure that your magnetic field is going to have like a toroidal symmetry. It's not going to depend on that. For like like the variation on the toroidal coordinate is not going to be very big. So I guess that also translates to the shape of the coils, but I'm not very familiar with how the coils would look. So that's what I would expect, but yeah, I'm not entirely sure.
And toroidal symmetry, it means that if you're like, I think isn't it like the Boozer coordinates are the one that sort of follow the movement of the flow, right?
Yes.
If you're in those Boozer coordinates, it means that you would be seeing a tokamak, right?
Yeah, exactly. Something very similar to a tokamak.
Right.
Yeah, exactly.
Great. Any more questions from the participants, or can we call it a day? One question for Tobias in the chat. Do you have in Estelle, do you have magnetic islands in the edge of Estelle?
It's not designed for that. So no, in principle, you shouldn't have. Yeah, it's not like in W7X, it was designed to have magnetic islands on the edge to work for the diverter, but yeah, no, and still, also you don't expect very high temperatures.
So you wouldn't want a diverter in Estel because you don't think that you'd get enough pressure to turn it into a reactor. It's really an experimental device, right? Because
yeah,
in a
exactly.
reactor, you really want a diverter.
Yeah, but yeah, I mean, again, I'm not very familiar with the technical details of Estel, but yes, as far as I understand, there is, well, at least not for an island diverter.
Okay. Great. One more chance for questions. Okay. So if we don't have any more questions, thank you so much, Katja.
No, thank you.
Wish you all the best for your new beginning in Greifswald, and look forward to the next talk.
Okay, thank you very much.
Which is going to be by Jose on superconductors next week.
Okay, looking forward to it.
Bye. Have a nice evening.